Good morning, friends and viewers. Thank you for watching this video. Uh, in today's video, we were talking about shear force and bending moment. Especially in solid mechanics or strength of materials, this shear force and bending moment comes into picture. And this is a very fundamental and important thing for mechanical as well as civil engineering students as well as diploma holders. So let us go with the shear force and bending moment. In this video, we are talking about the fundamentals of shear force and bending moment. So basic fundamentals, then we will go in the next upcoming video lessons, we will go through various problems in that and some numerical examples also we will go through it. But this video lesson is purely for shear force and bending moment fundamentals. So I have a PPT with you. I would like to share that one first, and according to this PPT, we will go through this lesson. Shear force and bending moment. I am Anand Padavala. I'm senior faculty member in the Department of Technical Education, Telangana government. So now, introduction. We have two figures here. Consider the beam subjected to transverse loads as shown in the figure. So let us take these two beams. These two beams are subjected to transverse loads. What do you mean by transverse load? Transfer load is the load acted on a beam perpendicular to its axis. The beam is like this and its axis is, longitudinal axis is like this. And if a load is applied like this, then it is called transverse loads. So these are the loads that given here. So when the load is applied, that is transverse load applied on these beams, what happens? Definitely there will be a bending. For example, if you see here, if I apply load here, because supports are here, it will deflect like this. Rather, I can say it bends like this. If you take this beam, where is one end is fixed, the other end is not fixed, it's other end is free. So when we apply a transfer load, what happens? This will bend like this. So this will bend like this and this will bend like this. So the deflection occurs in the plane same as the loading plane is called plane of bending. So if you see the loading here and the bending is also in that plane only. So then it is called a plane of bending. Now, in this class, we discuss shear force and bending moments in beams related to the loads. We will go through this. So, this is what a bending. Now, what is a beam? First of all, when we talk about shear force and bending moment in beams, first of all, what is a beam? A beam is a structural element. Beam is a structural element that primarily resists loads applied laterally to beam's axis. That means it's an element, it will resist the loads applied laterally. Laterally means, as we said, no transverse, that is perpendicular to its beam's axis, longitudinal axis. So the beam is basically, it's a structural element which will resist loads applied laterally on the beam. For example, if you take, this is a beam. The axis is like this. When we applied a load laterally like this, then it is supposed to resist that load. Then only we can put some load on this. If it will bend, then it is a failure. So our aim is not to bend. So without bending, what we have to do, that we have to take care while designing. So the mode of deflection is primarily by bending. When a load is applied here, for example, if you see the same thing, when we applied load like this, these are the transverse or lateral loads, then primarily what happens to this beam, it is subjected to bending only. So neither elongation nor compression, only it will bend. bending will take place. So this is what the characteristics of this beam. The load applied to beam results in a reaction at the beam support point. So now what happens, why it will bend like this? Because supports are here. So it will resist the beam. When the load is applied here, these two supports will resist the load. Whereas here there is no, what I mean to say, uh, reaction force, or that is supports are there. Therefore, what happens? It will bend like this. So beam is basically a structural element that primarily resists the load applied laterally to the beam's axis. Now, what are the various types of beams we have? So we have different beams. One is called cantilever beam. What is a cantilever beam? Cantilever beam looks like this. That means cantilever beam, for this beam, one end is fixed, the other end is free. When a beam is fixed at one end and free on the other end, then it is called a cantilever beam. So this is a cantilever beam. Second one is simply supported beam. What do you mean by simply supported beam? So it looks like this. In the simply supported beam, it is supported at both ends, this end as well as this end. Both the ends will be fixed. So both the ends will be, the supports will be there at the both the ends. So when we have supports at both ends, then that type of beam is called simply supported beam. Third one is overhanging beam. What do you mean by overhanging beam? So here it is overhanging beam. That means overhanging means if we have beam beyond the supports, if we have a beam beyond the supports, then it is called overhanging beam. So if you compare with the simply supported beam and overhanging beam, simply supported beams, the last point on both sides will be the support. Whereas in overhanging beam, the last part of the beam may not contain a support. So it should have some overhanging beyond the supports. The overhanging beam can be not necessarily both sides should be overhanging. It can be one side is fixed, the other side, one side is supported, the other side may be overhanging, or this side may be supported, or this side may be overhanging, or both sides may be overhanging. So anyway, it will be called as overhang. Whether it is single side or both the sides, this it is called a overhanging beam. That means beam should have it should run beyond the support. Then it is called overhanging beam. Continuous beam. What do you mean by continuous beam? If you observe in simply supported beam and overhanging beam, generally you have two supports. Suppose if you have more number of supports, then it is called continuous beam. For example, if you see, if you take this one is a continuous beam. So here, there are as many supports as are there. Therefore, if you have more than two supports, then it is called a continuous beam. Next one is fixed ended beam. The name itself indicates it is called fixed ended. Fixed ended means both the ends are fixed, then it is called fixed ended beam. So fixed ended beam like this. Cantilever beam, when compare with the cantilever beam and fixed ended beam, cantilever beam will have fixed end at one end and the free beam will have a fixed end and a free end. Whereas in fixed ended beam, you have both the ends are fixed. Then it is called fixed ended beam. Sometimes you have a combination beam. What do you mean by combination beam? Combination beam means it may consist of more than two beams. For example, in this example, you have a cantilever as well as simply supported. Sometimes you may have a overhanging and a cantilever beam. Like that, you may have, if you have a combination of more than one beam, it is called a combination beam. So there are 6 types of beams that we will be talking about in shear force and bending moment. One is cantilever beam, in which one end is fixed, the other end is free. Simply supported beam, both the ends are both you will have supports on both the ends. Overhanging beam, you may have one end or both the ends may have overhanging of the beam. That means the beam will run beyond the supports, either in one end or on both the ends. Then it is called overhanging beam. Next one is continuous beam. When you have more than two supports, then it is called a continuous beam. Fixed ended beam means both the ends will be fixed, and combination beam means any combination of two beams is called a combination beam. These are the types of beams. So we'll continue with the types of beams. I have given some practical examples here. For example, if you take, this is a car shed. Car shed, this is a beam. So can you guess what kind of beam it is? Yes, there you are. It is a, here if you see, one end is fixed here. The other end is free. So one end is fixed, the other end is free. Which type of beam it is called? It is a cantilever beam. Next one. No, I think in Hyderabad we have gone through so many projects like this, metro rail projects. So there will be two pillars, and above that you will have some load from this place to this place. What kind of a load it is called? So you have only two supports when we are talking about. There will be a gap between this this plate and this plate. What I can say, I am talking about the upper one. So these are the two supports and one plate. This is ductor, whatever we will say it is. So this is, so what kind of, when you have two supports, then it is called simply supported beam. Can you guess what kind of a beam it is? Is it a cantilever beam? No. It has two supports here and some overhanging here. So it is called overhanging beam. Next, see what kind of a beam it is. So this is a single bridge. Single bridge runs on how many supports? More than two supports. Then what kind of a beam it is called? This bridge is called. So the entire setup is called, yes, when you have more than two supports, it is a continuous beam. Now, so here take about this I beam. This is I section beam. I section beam, if you take, this is fixed here and this is fixed here. So I think you can easily guess what kind of beam it is. It is a fixed ended beam. It is a fixed ended beam. So these are some of the practical examples of types of beams. Now we will talk about types of loads we have. What are the various types of loads we have? So we have, basically there are many types of loads. Our discussion is only for three types of loads. One is a point load. Second one is uniformly distributed load. The third one is uniformly varying load. So one is point load. This is also called as concentrated load. Concentrated load or point load. Both the names are given to this one. Second one is uniformly distributed load. Shortcut we will call it as a UDL. And uniformly varying load, we will call it as a UVL. UVL means uniformly varying. So what are these? What is a point load? Point load means it acts at a point on the beam. For example, if you take, this is a beam. On this, you have given some weights here and here. So where it will act at a particular point. Actually, if we take that the thickness of these two weights are negligible when compared to the beam, then it acts as a point load here. Point load means it will be concentrated load or point load. It acts at a particular point on the beam. Then it is called particular point, means the entire transfer, entire span, not entire span like this, you should not, at a particular place. If you see from the front view, the load is here and the load is here. So when it is applied on a particular point, then it is called a point load or a concentrated. Second one is uniformly distributed load. What do you mean by uniformly distributed load? If the load is there for the entire span, for example, if you take this is the beam and this is a steel plate and concrete load, if we take, generally what we will do is when we go for a slab, when we make slabs, that means with the help of pillars, pillars are the supports, and we will have an entire span. We will give the concrete with some width, concrete, steel and concrete mixture. So this width, this entire span will have a uniformly distributed. The load, the entire span will be uniformly distributed. Uniformly distributed load will be indicated like this. That means this load is for there for entire span. That's why it is called uniformly distributed load, or UDL. Third one is uniformly varying load. What do you mean by uniformly varying load? That means the entire load varies uniformly. That means it is a varying load, but the variation will be uniformly done. For example, here is this is a beam. These are the two pillars on which I want to make a wall. I want to make a brick wall like this. Now, if you see the brick wall, the load is varying. It starts from 0 here, this point, till end. It is varying. The load is varying, but the variation is not abrupt. The variation is uniform for the entire span. So this is called uniformly varying load. This is what. So when we write a block diagram, or what we call it as a free body diagram, then this is a beam and this represents uniformly varying load, UVL. This is called uniformly varying load. So these are the basically three types of loads. One is a point load or concentrated load. The second one is what we call it as a uniformly distributed load, UDL. And the third one is uniformly varying load, that is UVL. Now we will come to what is shear force. So before we discuss and before we define what exactly the shear force is, so let us consider a beam. Now what kind of beam it is? Yes, you guessed, you have two supports here. And what type of load you have? A point load here. So this beam is a simply supported beam because it has two supports at the ends, both the ends, and also you have a point load at the center, for example, if you take. So figure shows a simply supported beam AB carrying a load of 1000 newtons or 1 kilonewton at its middle point. C is the middle point of AB. Now, can we calculate the reactions at the supports? Obviously, they are equidistant. Therefore, the reactions will be 5,000 each, 500 each, sorry, 500 each, because the total load is 500, 1,000, 1,000. Therefore, this load, this reaction will bear 500 newtons and this reaction will bear 500 newtons. So, because it is at the middle point. If it is not at the middle point, then the load distribution will be varied. So hence reaction at A and reaction at B will be 500 newtons each. So we can say simply like this, RA and RB like this. Now we are trying to understand what exactly the shear force is. Now imagine the beam is divided into two portions by a section. Now let us see that. Let us imagine, we are not cutting any point. Let us have a section, XX section, at this point to understand what is shear force. Now we will take a section XX, left hand side and right hand side. If you take the left hand side, what will be the resultant load? There is only one load is here. To the left of this XX section, there is only one load, that is 500 newtons, and that is vertically upwards. So what will be the resultant? Because single force is that only with the resultant. Resultant will be 500 newtons up vertical upward direction. That is the resultant load of the reaction to the left of XX. Now we will come to the right hand side of the x section. There you have two forces. One is 1000 newtons downward and 500 newtons upward. So now resultant of the load reaction right is 1000 downward force and 500 upward force. So what will be the net resultant? Because 1000 downward and 500 upward, the net resultant will be, or resultant force will be 500 newtons downward. So here the resultant load to the left is 500 newtons upwards. The resultant load on the right side is 500 newtons downwards. So the resultant force acting on any one parts normal to the axis of the beam is called shear force at that section. So the resultant force acting on any one of the parts normal to the axis of the beam is called shear. That means if you want to know shear force is nothing but this is. It will have a shearing effect on the beam. That's why it is called shear force. See, when it is acted along the line of axis, you will have a elongation or contraction. That is, either it may be tensile force or a compressive force. But here it is a shear force because it will create a shearing effect on the beam. That's why it is called shear force. At this section, we want to know the shear force. The shear force at this section is 500 newtons. So at this section, we want to know it is 500 newtons. So let us try to define the shear force. Shear force is the force in the beam acting perpendicular to the longitudinal axis. As I said, no. So it is acting perpendicular to the longitudinal section. So shear force is the force in the beam acting perpendicular or vertical to the longitudinal axis. Here is a definition. Shear force of a beam at any section is the algebraic sum of the vertical forces acting to the right or left of the sections. That's what we have done in the previous example. So on the left side we have 500 newtons, on the right side, because the left hand only one resultant for one force, that only resultant force. On the right hand side we have two forces and the resultant forces is also 500. So shear force of a beam at any section is the algebraic sum of the vertical forces acting to the right or left of the section. So this is what. So if we want to see, so this is the resultant force here and the resultant force of the 500 newtons. So shear force of the beam at any section is the algebraic sum of the vertical forces acting to the right or left, not both. Either if you want to calculate the shear force, you should take either left or right. Any one side you should take, not both the sides. Then we will get a shear force at that particular section. Now, you may get one doubt. Here it is 500 newtons upward and here it is 500 newtons downward. So when we talk about load is also a force. So when we talk about shear force is a force. So we should tell the direction. So whether it is a positive or a negative or upward or downward, we have to tell. So what is the direction of the shear force at this particular section? So we have some sign convention for that. So sign convention for shear force. Shear force at a section will be considered as positive. So we will talk about positive and negative. Shear force at a particular section will be considered as a positive if resultant of the forces to the left section is in the upward direction. In the left section, if it is upward direction, left side and upward direction, then it is a positive. Or if you take the resultant force on the right side and downward section, then it is also a positive. So when you will take a shear force as a positive one, if you take the left side section, it should be upward. If you take the right side section, it should be downward. Then we will take it a shear force as a positive. So in the previous example also, in the left side you have upward direction, the down side you have a downward direction. Therefore, both the things considered to be positive. Therefore, if you take either right side or left side, it will give positive shear force. So here is a schematical I have given here. This is x-axis section, this is left side and down side. So shear force will be positive if this is upward direction, this is downward direction. Now, shear force of a section will be considered as a negative, just opposite to the what we have discussed. If the resultant forces on the left hand side direction is downward direction, that means left and downward, then it is a negative. And if we take resultant force in the right and upward direction, then it is called as a negative. So this is negative and this is negative. So here it is schematically. Shear force will be negative if the left side is downward direction and then the right side if it is upward direction. In the previous example, whether it is a positive shear force or negative shear force, it is a positive shear force because in the left hand side it is upward direction, in the right hand side it is downward direction. Both are 500 newtons, so you should take as a positive. So here is the sign conventions are very important. When we draw shear force and bending moments, these sign conventions are very important. So simply, so left hand side upward positive, left hand side downward negative. Right hand side downward direction positive, right hand direction upward direction is negative. Simple. Now we will go to what is a bending moment. To understand a bending moment, let us say take the same beam, a simply supported beam with a point load at center, that is 1000 newtons. We know that the reactions have 500 newtons each. Already we have seen this one. Now imagine the beam is divided into two portions by section XX. Here is XX section. So how the section is made? It is 1 meter. For example, take entire span is 4 meters. So A to C is 2 meters and C to B is 2 meters. Let us example take a section 1 meter from A. It is 1 meter from A if you take. So this is the 1 meter from A. Now we will try to calculate the moments. What is a moment? First of all, moment is nothing but force into perpendicular distance. For example, I want to calculate a moment of this force at any point. That means we have to find out the moment, we need a point. Moment about that point. If I want to find out the moment of this 1000 newtons with respect to the point A, that means what I have to calculate? The force into displacement. That means perpendicular distance from this A. Not displacement, it is a perpendicular distance. That means force is 1000 newtons into the distance is AC. Perpendicular distance is AC. Therefore, AC is 2 meters. 2 into 1000 will be 2000 Newton meter. That moment it will create the 1000 Newton force with about a point A. This is a moment. I think we have seen in the engineering mechanics. Now let us try to find out the moment of all forces. All forces means load and reaction to the left x-axis section. Now try to find x-axis section. To the left we will try to find out the moment about this force. Now we know that how many forces are there? Only one force. Moment about this section at this point, if I want to find out the moment, so I want to find out a moment at x section. So how many forces are there? To my left, it is only one force, that is RA, that is 500 newtons. So what is the moment of this force about this point? Is nothing but force 500 into perpendicular distance. It is 1 meter. So 500 into 1, RA into 1, that is 500 into 1 Newton meters. And which type of movement it will create? It is creating clockwise movement, clockwise direction. The movement direction of the movement is clockwise. Movement is also a vector quantity. So It is a clockwise direction it is making. Now we will talk about the right hand side of the XX section. In the right hand section, you have two forces. One is 1000 Newton and 500 Newton. So when we talk about the two forces are there, then we have to find out the net bending moment. The net moment it will create. For example, net moment means this 1000 Newtons, how much it will create? 1000 into what is the perpendicular distance from this place to this place? 1. 1000 into 1, it will have which type of direction? Anti-clockwise direction. Therefore, you have what? Sorry, this is a clockwise direction. 1000 newtons will create a clockwise direction. See here the clockwise direction, and this 500 newtons RB will create anti-clockwise direction about this one. So RB into 3. Why 3? Because 2 meters plus 1 meter. Total is 3 meters. 3 meters into 500 minus, this is anti-clockwise. Generally, we will take anti-clockwise as positive and clockwise as negative. So RB into 3, that is 500 into 3 minus 1000 into 1, that is 1000 into 1. That is 1500 minus 1000, 500 Newton meters anti-clockwise. See, if you see here, the movement on the left hand side, we have 500 Newton meter clockwise. In the left side, we have a 500 Newton meters anti-clockwise direction. So if you want to talk about the bending moment at a particular point, is nothing but the algebraic sum of the total movement either on the left hand side or on the right hand side. So it is the bending moment at a section is the algebraic sum of the moments of forces reactions acting on one side of the section. So if you take either this side section or this side section, it is 500 Newton meters. As far as the directions are concerned, we will, when we discuss about the sign convention of bending moment, there we will talk about the direction. So this is what the bending moment of section. The magnitude of the bending moment is 500 newtons at XX. Now, hence the tendency of the bending moment at XX section is to bend the beam and produce concavity on the top. For example, you see here how this is creating a clockwise movement here. You talk about left hand side from A to XX section, the beam will bend like this, clockwise direction. In the anti-clockwise, in the right side, it will bend like this because it is a 500 meters Newton meters anti-clockwise, 500 Newton meters clockwise. That means both you will have a concavity. See here. Here you have a clockwise direction. Here is the anti-clockwise direction. At XX section, you will have a concave bending. So at the top. So let us try to define what is a bending moment. Bending moment is a measure of a bending effect that can occur when an external force or a movement is applied to a beam. So beams are not only subjected to forces, they may subjected to bending moments also. So when a beam is subjected to external force or a movement, then the bending may takes place. So bending moment is a measure of bending, how much effect of bending has happened or occurred to that beam when it is subjected to external force or a movement. So here is the definition of a bending moment of a section. Bending moment of a beam at a section is the algebraic sum of all the movements to either side of the section. If you take a section, there will be left hand side and the right hand side. Take any one section, not both the sides. Any one side of the section you should take. If you either take left hand side or right hand side. So the bending moment of a beam at a section is the algebraic sum of all the moments to either side of the section. So this is what a bending moment. Now, sign convention of a bending moment. So we have in the earlier example, we have seen 500 Newton meter clockwise and 500 Newton meters anti-clockwise. Which direction we have to take? So here we have a sign convention for bending moment. So bending moment at a section will be considered as a positive. So positive bending moment, when we say if the bending moment to the left of the section is in clockwise direction. So if the bending moment to the left of the section in clockwise direction, left hand side and clockwise direction, then we will call it as a positive bending moment. And the bending moment in the right side and anti-clockwise. So when we take right side and anti-clockwise, then also it is a bending moment is a positive. So in the example what I have seen, left hand side clockwise direction and right hand side anti-clockwise direction. So both will give positive bending moment. Such type of bending moment is also termed as a sagging bending moment. Sagging bending moments, when the positive bending moment is there, then we will call as a sagging. That means a beam will bend like this. On the top beam will bend like this. So this is what we have. So bending moment at a section will be considered positive if the bending moment at the section will tend to bend the beam in a curvature of having a concavity at the top. Here we have a this thing. See here, sagging or a concavity. That means left hand side of the section you have a clockwise direction. Right hand side of the section you will have a anti-clockwise direction. So the entire beam will bend like a concave beam. Concavity will be there on the top. So when it appears to be a concavity, then it is called a positive bending moment or a sagging. Now, when bending moment of section will be considered as a negative, when it will be negative, opposite to the positiveness. That is, if the bending moment to the left section is anti-clockwise, left section is anti-clockwise direction, or to the right section is clockwise direction, right direction, clockwise direction, then it is such then it is called as a negative bending moment. Such type of bending moment is termed as a hogging. Hogging bending moments means it will bend like this. Earlier it is like this. Now it will be like this. Hogging. So when it like this, it is hogging. In case of negative moment, beam will bend in a curvature with a convexity at the top. Earlier positiveness, concavity. Now when it is negative bending moment, convex and convexity will appear at the top like this. So hogging. So in the left hand side you have a anti-clockwise, and the right hand side is a clockwise. So both will give a hogging or a convexity curvature on the top. So when a beam will bend like this, when a beam will bend like this, it is a negative. When a beam bend like this, it is a positive. So this is what we have. I want to tell you that suppose this is a beam. So when it is bending like this, then it is a positive. When it is bending like this, then it is a negative. So these are the basic fundamentals of bending moment, shear force and bending moment things. So in this lesson, we have seen what is what are the types of beams we have, and also what are the types of loads we have, and what is a shear force, and what is a bending moment, and what are the sign conventions of shear force, and what are the sign conventions of a bending moment. These are the fundamental things. So I'll stop here. Before I stopping, I would like to share one video about the understanding of shear force and bending moment. I like this video. This video is available in YouTube. Thanks. I'm sharing here. I'm really thankful to the original owners of this video for giving an opportunity to share this video. Thank you very much. So now let us go through the video. Here it is. Share the computer sound. Yes. Here it is.
Shear force and bending moment diagrams are powerful graphical methods that every mechanical and civil engineer should know how to use to analyze a beam under loading. In this video, I'll explain exactly how to master these diagrams, and we will see how they can be used to understand how a beam is loaded. I want to start by explaining what shear forces and bending moments actually are. When a beam is loaded, internal forces develop within it to maintain equilibrium. These internal forces have two components. We have shear forces, oriented in the vertical direction, and we also have normal forces, which are oriented along the axis of the beam. If the beam is sagging, the top of the beam will get shorter, and so the normal forces in the top of the beam will be compressive. The bottom of the beam will get longer, and so the normal forces in the bottom of the beam will be tensile. Each of the tensile normal forces has a corresponding compressive force, which is equal in magnitude but opposite in direction. As such, these forces don't produce a net normal force, but they do produce a moment. This means we can conveniently represent the internal forces acting on the beam cross-section using just two resultants. One, shear force, which is a resultant of the vertical internal forces, and one bending moment, which is a resultant of the normal internal forces. This is a very common way of representing the internal forces within a beam. Drawing the shear force and bending moment diagrams is just figuring out what these internal forces are at each location along the beam. These resultant shear forces and bending moments will depend on the loads acting on the beam and the way in which the beam is supported. Beams can be loaded in a number of ways, the most common being concentrated forces, distributed forces, and concentrated moments. Beams can also be supported in a number of different ways. They can have pin supports, roller supports, or be fully fixed, which each restrain the beam in different ways. Pin supports prevent vertical and horizontal displacements, but allow rotation. Roller supports prevent vertical displacements, but allow horizontal displacement and rotation. Fixed supports prevent all displacements and rotation. If a certain degree of freedom is restrained at a support, we will have a corresponding reaction force or reaction moment at that location. For example, rotations are permitted for a pin support, so there is no reaction moment, but displacements in the vertical and horizontal directions are prevented, so we will have horizontal and vertical reaction forces. So how do you determine the shear forces and bending moments within a beam? There are three main steps we need to follow. First, we draw a free body diagram of the beam. This shows all of the applied and reaction loads acting on the beam.
Hello, Alex Cole here with Bobcat Kim. So in this video, we're going to work.
The next step is to calculate the magnitude of the reaction forces and reaction moments at all of the beam supports. We do this using the concept of equilibrium. To maintain equilibrium, all of the forces in the vertical and horizontal directions should cancel each other out. Similarly, all of the moments acting at every point along the beam should cancel each other out. This gives us a set of simple equations we can solve to calculate the reaction forces and moments. If we can calculate all of the reaction loads using the three equilibrium equations, the beam is said to be statically determinate. For some beam configurations, like this one shown here, we won't be able to calculate all of the reaction loads because we have too many unknowns and not enough equilibrium equations. In this case, the beam is said to be statically indeterminate. This beam has 4 reaction forces, but we only have 3 equilibrium equations. To solve this beam, we would need to use slightly more complicated methods and consider boundary conditions. In this video, I will only cover statically determinate cases, where we can use the equilibrium equations to calculate all of the reaction loads. Once we have calculated all of the reaction loads, the third and final step is to figure out the internal shear forces and bending moments at every location along the beam. To do this, we will use the concept of equilibrium again. If we cut our beam at any location, the internal forces and moments need to cancel out the external forces and moments so that equilibrium is maintained. This allows us to easily calculate the shear force and bending moment at each location along the beam. All we need to do is start from one side of the beam and move the location of the cut along the beam, calculating the shear forces and bending moments as we go. Now is a good time to define the sign convention we will be using. Applied forces will be positive if they are acting in the downwards direction. For shear forces and bending moments, the positive sign convention will be as shown here. If the beam is on the left side of our cut, shear forces pointing downwards will be positive. If the beam is on the right side of our cut, shear forces pointing upwards will be positive. Positive bending moments will be those that put the lower section
Okay, friends, I think you have understood some concepts of the